All right, today we're going to continue talking about graphs and their relationships to first and second derivatives. The first problem here, we want to determine which is f prime and which is f double prime, f prime double prime. Here only has 2, but we have enough information to know if we have a quadratic, its derivative is going to be linear. So this is going to be our original graph. This is going to be the derivative of that. Also things like the slope here is 0, which is why the derivative is 0. The slope is decreasing and then it's increasing, which is why the derivative is negative, then positive. Here we've got a cubic function, a squared function, and a linear function. So this one's going to be my original graph. The parabola is going to be the first derivative, and the line is going to be the second derivative. So for question 2, we have y prime equals 6 times x plus 1, x minus 2 squared. And we're going to find all the points where it has a maximum, minimum, and a point of inflection. So for the maximum and minimum, I already have the derivative. So I'm going to do my number line analysis. Okay, so this one's going to be negative, or it's going to be 0 at negative 1. This one's going to be 0 when x is a two. So this one's going to be negative 1 and 2. So this one's going to go from negative to positive. This one, for every number except for 2, it's going to be a positive value. So this is going to be positive all the way across, which means this one's going to be negative, 0, positive, and positive. So this one is decreasing, increasing, increasing. So we have a minimum here, and that's it. So there is no maximum. There is a minimum when x equals negative 1. Points of inflection, we're going to need the second derivative. We'll need to do the product rule here. I'll just lump the 6 in here. Okay, so that one prime. Okay, so there's our product. So the derivative of this is just going to be 6. Here I'm going to have, I'll bring the 6 out front, 6 times 2x minus 2 times the derivative of the inside, which would be 1, plus, or times x plus 1. Okay, I'm going to factor out an x minus, a 6 and an x minus 2. Okay, which here is just going to leave me with 1 x minus 2. Here I'm going to have, pull this out, a 2 times x plus 1, so it's going to be 2x plus 2. So this gets pulled out, this gets pulled out, 2 times x plus 1, 2x plus 2. So we have 6x minus 2, and then we have x plus 2x is 3x, and minus 2 plus 2 is 0. So this is going to be 18x times x minus 2. Do our number lines. So this one is 0 at 0. This one is 0 at 2. This one's going to go from negative to positive. This one's going to go from negative to positive. So positive or negative, negative is positive. Positive, negative is negative. Positive, positive is positive. So this one is concave up, concave down, concave up, which means there are 2 points of inflection. One at 0 and one at 2. So here's a old AP problem. So we have a function f of x equals x over the square root of x squared minus 4. The domain, there's 2 issues. I can't let the denominator equal 0, and I can't take the square root of a negative number. So what I need is for x squared minus 4 to be greater than 0. It can't be equal to 0 because that makes a 0 in the denominator, and it can't be less than 0 because it makes it so we're taking the square root of a negative number. So this is going to be 0 at 2 and negative 2. If I plug in a number in between those, like 0, then it's going to be negative. So we need x to be greater than 2 or x to be less than negative 2. The equation for each vertical asymptote, that makes the denominator 0. So what makes x squared minus 4 equal to 0? 2 and negative 2 are our vertical asymptotes. The horizontal asymptote is the limit as we go to infinity and negative infinity. And in a lot of cases, that's the same thing. This one, however, is not. So as I go to infinity, if I take the square root of an x squared, that's essentially a degree 1. So we have a degree 1 over a degree 1. So as we go to infinity, this is going to be 1 because we're going to have infinity over infinity there. For negative infinity, however, the denominator is always going to be positive, but if we're going to negative infinity, this is going to be negative. So this one, it's going to have the same relative value, but it's going to be a negative over a positive, which will make that limit negative 1. In this figure, we have the graph of f prime of x. We don't have the graph of f, we have the graph of the derivative. The domain is from negative 10 to 10. So here's our graph. So here it says for what values of x does the graph have a horizontal tangent? And your brain is going to go over there and there and there. But it's not, because we want the graph of f, not f of x. So my tip for you, because looking at this, you're looking at a graph and you want to see things a certain way. So I'm going to take this information from the graph and put it in a number line so I don't have to see the graph, I just see what the graph is telling me. So we're going from negative 10 to 10. The derivative is 0 when this graph is 0. So it is 0 at negative 7, negative 1, 4, and 8. Okay, then the graph, the derivative is below the x-axis, which means it's negative, positive, negative, positive, then negative. So that's the information this graph is telling me. Now, ignoring the graph, this means my original graph is decreasing, then increasing, then decreasing, then increasing, then decreasing. So we can answer the questions not looking at this, but looking at the number line, because this has the information I need. And it's easier to interpret because we know what all of this is rather than looking at this graph. So where does it have horizontal tangents? Well, where the derivative is 0. So at x equals negative 7, x equals negative 1, x equals 4, x equals 8. Has horizontal tangents because the derivative is 0. Where does it have a relative maximum? Well, we've got a minimum, a maximum, a minimum, and a maximum. So we have a maximum at x equals -1 and at x equals 8. Justify, because f prime of x switches from positive to negative. Remember, you have to say f prime, and it's switching from positive to negative. Now look at what that looks like on this graph. We're saying that's a maximum and that's a maximum. And that, again, it's hard to get your brain to think that way. So taking this information and putting it on a number line makes that a lot more accessible. For what values is the graph concave down? So now we want to look at second derivative. Okay, the second derivative is going to be the derivative of this. So where this graph has a maximum or minimum, the second derivative is going to be 0. So at -3, at 2, and at 6, my second derivative is going to be 0. Where this graph is increasing, this function is positive. Okay, the derivative is positive. If it's decreasing, it's negative. Increasing is positive. Decreasing is negative. So this graph is, the original graph, which we don't have, is concave up, concave down, concave up, concave down. So now, where is the graph concave down? Between -3 and 2 and 6 and 10. And it's important to they gave us a range of values, so you don't want to say to infinity, you want to say until 10. Okay, justify your answer. Here's all I want you to say. How do we know things are concave downward? Because f double prime of x is less than 0. We got there from going, well, we wanted to look at where the first derivative was decreasing, and that's how we actually did it. But to justify it to College Board, all you want to say is because the second derivative is less than 0. Don't launch into a essay about how you arrived at that answer. Just say that. And our inflection points are going to be where we switch concavity. So here, here, here. So that's going to be at x equals -3, x equals 2, and x equals 6. Why? Because f double prime of x switches signs. This next problem, we have a table with a lot of information. So we have x from 0 to 3, so 0, 1, 2, 3. We have the function values, we have the derivative values, and what's happening to the derivative, the second derivative, and what's happening there. So we're going to try to draw a graph. So I'm going to first actually, before we do that, we have our function values, 0, -2, 0, and 3. So I'm going to start there. Okay, so we're just going from 0 to 3. So at 0, our function is at 0. At 1, our function's at -2. At 2, our function's at 0. And 3, our function's at 3. Now we want to connect the dots using the information here. So I'm going to put this on a number line. So my derivative is -2, 1. At 1, it's 0. Then it is positive. It's undefined here, but our graph is continuous. And from 2 to 3, it's also positive. Looking at the next row, it's always positive, so that means the graph is always concave up. Okay, so we are, sorry, it should be positive, negative, positive, positive. So it's decreasing concave up to -1, increasing concave up to 1, and then it is increasing concave up to here, which is why that derivative is not defined there, because we have a cusp if it goes from a concave up increasing to a concave up increasing. The absolute maximum and minimum. The absolute max is going to be that point there, so 3, 3. My absolute minimum is going to be this point here at 1, -2. So we have a graph that has the function h. We are going to graph the derivative of h. And then it mentions that h prime is undefined because there's a cusp. So the derivative is the slope. So here the slope is always a constant +1 until we get here where the derivative is undefined. So I'm going to make that a negative point. For this, it's decreasing, then it's increasing. We have it 0 here. And if I look at this, it's not an x squared, it's something less. So we'll say it's about there, just an estimate for our derivative. Is it correct to say that h prime of 1 is infinite? No, that only applies to asymptotes. Okay, is h continuous at 1? Yes, it is. Is it differentiable? No. So yes, continuous, not differentiable. This next one, we have the derivative graph, and we're going to graph the original function using the fact that we have an initial condition of g of 0 is 3. So I'm going to take this information and I'm going to put it on a number line. So we have the graph of g prime. G prime is 0 at -1 and 3. It is positive to 1. It is negative between -1 and 3. And it is positive after that. So my original graph that we're about to draw is going to be increasing, then decreasing, then increasing. We're going to have a maximum at 0. We're going to have a minimum at 3. And again, taking this information and putting it into a number line, now we know what this looks like. It's very hard to say, well, the graph is decreasing here because you're looking at a graph that's increasing, but the original graph, because the derivative is negative. So taking this and putting it on a number line separates that idea. For the second derivative, we're looking at the derivative of this graph. So this one goes from decreasing to 0 to increasing, and that happens at 1. The slope is 0. So this is negative, then it is positive, which means on my original graph, we're concave down to concave up. And you can kind of piece together, it's concave down and it goes increasing to decreasing, it's concave up, decreasing, increasing. So this, the green parts there kind of build the structure. So we have a maximum at -1. So I'm just going to put a dot up here. So this graph is going to be, and we have an IP here. We have a minimum at 3. Let's put a dot somewhere there. So our graph is increasing concave down, then it is decreasing concave down at At 1, it switches to concave up. At 3, it starts to increase. For this one, we have the graph of y, and we're going to graph the derivative. So this one has a slope of 1, so my derivative is going to be 1. At the corner, the derivative doesn't exist. Here, this is a level line, so its derivative is going to be 0, but the endpoints are open dots because it's not differentiable at a corner. This one, our derivative here is 0. It's going to be positive here, negative here. But if you notice these tangent lines, the slope is becoming vertical, which means the derivative is going to be infinite. So this one, as we approach that point, it's actually going to reach an asymptote. And same there. Now we have the same graph, but what it represents is different. This one shows this thing is the derivative, and we want to graph the original function. So let's take what we have here and put it in a number line. Okay, what does this tell me? This derivative never crosses any axes. It's always positive, which means my derivative is always positive. My second derivative, and we're going to look at where this one is increasing and decreasing. We don't have a derivative at 1 or at 2. It's going to be 0 at 3 because that's going to be a maximum. So this one is going to be, this slope is positive, so this is going to be positive. This slope is 0, so its derivative is just going to be 0 there. So there's no concavity. This is increasing, so this is positive. This is decreasing, so this is negative. So this graph is going to be concave up, level, concave up, well, just no concavity there, and concave down. So we're starting at 0, 0. We're concave up. Then here, if this is the derivative, then we just have a straight line. Then we are concave up, increasing to 3, and then concave down, increasing. For all x in the closed interval 1, 4, f function g is concave upwards, which of the following tables could be the values of g? This means that the slopes are increasing. So if we look at these change in y versus these are all 1. So the change in y here, it's going up 3, up 1, up 4. So the slopes are not increasing. Here it's 2, 3, and 5. This one is, but I want to compare it 5 to 5. Nope. Here is 2, 2, 2. So those slopes are not increasing. Here is the only one where the slopes are increasing. That is it for the third day of graphing.